In this ICFD++ tutorial, we're going to walk you through the steps to set up and model the flow of air in a thrust reverser bucket geometry. We will demonstrate the setup using the new Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. The purpose of this example is to show how the stator blade source term model along with the porosity model can be used to represent the turning mechanism inside a thrust reverser bucket without modeling the actual stator geometry. The source terms are enabled in a specific region of the mesh, and they introduce pressure loss and area blockage effects that are analogous to the presence of a row of stator blades. These source terms will be enabled in the region where my mouse is currently hovering. This example involves running 4 separate simulations. The first one will involve no source terms. The second one will activate the stator blade model only. The third section will enable both the stator blade and the porosity model, and in the fourth section we will only activate the porosity model. Before starting this example, I will briefly cover the new features and components of the ICFD++ AUI for our first-time users. For a more in-depth understanding of the ICMP AUI features that are common across all Metacomp software, you can click on the ICMP AUI demo link that will show up at the side of this video, or by referring to the ICMP AUI section of your ICFD++ documentation. First, the ICFD++ interface is composed of 5 items. The menu bar, where my mouse is currently hovering, this is where you would typically load and save your input file, etc. The toolbar has shortcuts to some commonly used functions and controls. Then the canvas, where the geometry or solution can be displayed. And then the notebook panels, which currently shows the ICFD++ setup steps. And the action panel, where much of the problem setup takes place. Within the notebook panel, ICFD++ shows an action tree or setup wizard which can guide you step by step through the various parts of the problem setup. There are also one or more information trees. In this case, we see the groups and boundary families tree and the boundary conditions tree. Each item in the action tree or information tree has corresponding items that show up in the action panel. This is where the user is given specific choices about the problem setup based on information supplied in previous panels. All panels are dockable and resizable so the user can customize the interface. Next, I'll briefly cover the mouse controls. The mouse is used to control the view of the geometry and the mesh within the canvas. Holding down the left mouse button and moving the mouse up, down, or left and right will rotate the geometry about its horizontal or vertical axes. Holding down the middle mouse button and moving the mouse up, down, and left and right allows you to translate the geometry up, down, and left or right. Holding down the right mouse button and moving the mouse left or right will rotate the geometry about the axis normal to the screen. And then holding down the right mouse button and moving the mouse up or down will zoom the view in or out. Next, I will open up a new AUI and start the case setup from scratch. In Linux, you can launch the AUI by typing mcfd AUI in a command shell. The user interface will open and we will see the first item in the action panel. The first panel prompts us to choose a working directory. In Linux, the default directory location is where you launch the user interface. Next, I will press OK to select the current working directory. We can accept the message in the pop-up box, and ICFD++ will generate an eGroups file so that we can display separate cell groups in the AUI. At this point, we can select Yes to both analyze our grid files and read the BC family file and the cell groups file. We will keep the selection of the number of cell groups set to the default. In this case, it's 2. We will not need to read the interior BC's file, so we can press OK at the bottom of this panel. And we can press OK in the pop-up box. Here we will see information about the cell type and the cell count and the BC selector names, etc. We can simply press OK to both of these boxes. Then focusing our attention back to the left side of the screen, we see the next item on the action tree is the Cell Types and Volumes panel. The first option at the top specifies how the code will react if it detects negative cell or cell component volumes. We can keep this option set to its default, which is the cell component option. The rest of the panel is populated according to how the mesh files were interpreted. We will not need to change these settings, so we can press OK in this box. Next, we'll see the General Problem Definition panel. We will be solving a viscous, turbulent, single species, non-reacting flow problem. And this falls into the category of a general fluid problem. So we'll select that option. We will also choose No for using a problem setup wizard, and then we can press OK. Next, we'll see the CFD problem definition panel, and here we choose the following options. For a fluid type, we'll choose the option of gas. For the species content, we'll choose single species. Below, we see a question of whether or not the flow is compressible, and we'll select yes for this option. In this case, the gas, we'll select perfect gas type. For the flow speed, we'll select mostly below Mach 0.5. For the questions of whether or not the flow is viscous or turbulent, we'll leave those set to yes. For specifying additional flow physics, we'll select the option of no, and in this case we'll run a steady state simulation. Now we can press OK. Next, we'll see the additional specifications panel. Here we'll choose no to all of these options, and we can press OK. Next, we'll see the equation properties panel. In this case, we'll keep the preconditioning option turned on. You'll also see a pressure base option. So we use preconditioning. We'll also use the two equation realizable K epsilon turbulence model. And we'll choose no for defining passive scalars and press OK. Next, we'll see the physics source terms panel. This panel allows us to introduce various types of source term effects. In part 1 of this example, we will choose no to all of these options. In part 2 of this example, we'll need to select yes, and here we'll enable a stator blade model. In part 3 of this example, we'll enable both a stator blade model and a porous media model. In part 4 of this example, we'll enable the porosity model only. At this time, we will go through the setup with both terms activated, and the user can repeat the process with only the source terms that are needed to complete each section of this example. With both terms activated, we can press OK. Next, we'll see the reference quantities panel. Here, we'll solve the case in dimensional mode, and we'll also use SI units. And we can press OK at the bottom of this panel. So next we'll see the fluid properties panel. Here we can activate and press the edit button to define the fluid type. In this case, you'll see the default fluid is air. We press OK to accept the properties for air. In this case, we can keep the base pressure set to 0.0, and we can keep the remaining settings for air. And press OK. So next we'll see the porous media source term model. So we can check the box, and we will specify which cell groups in which to activate this source term. Here, the options you'll see are all groups, group number 1 only, group number 2 only, all groups except group number 1, and all groups except group number 2. In this case, we'll activate the porous media source term in group number 2. So we'll select that option. To give some background on this model, a porous media can be described by resistance coefficients, where three coefficients corresponding to the three coordinate directions are used to describe the inertial and viscous resistances of the porous media. At the bottom of this panel, we'll see a principal axis conversion tool. This is available to account for any misalignment between the porous media principal directions and the global coordinate system in which our geometry is displayed. Here, we will open the principal axis conversion tool, pressing the plus button. We'll see that three inertial resistance coefficients can be entered at the top of this section of the panel, and three viscous resistance coefficients can be entered below this. The two direction vectors that are requested at the bottom of this panel correspond to the directions of each resistance coefficient in the porous media, and this is defined relative to the global coordinate system. Direction vector 1 corresponds to the directions corresponding to coefficients C1 and D1. Direction vector 2 should be orthogonal to vector 1 and corresponds to C2 and D2. And direction vector 3 is computed internally, and this is the final orthogonal vector that corresponds to C3 and D3. Next, we will need to enter the following inertial resistance coefficients in the principal axis conversion panel. For the inertial resistance coefficients, we'll enter 0.5 for the first one, 8.0 for the second one, and 8.0 for the final one. For the viscous resistance coefficients, we'll enter 0 for each coefficient. Next, for the direction vectors, we will enter unit vectors corresponding to the rotation of the principal axis of the porous media relative to the global coordinate system. For the first direction vector, we'll enter negative 0.7071, for the second value, and for the third value in the first vector, we'll enter 0. For the second direction vector, we'll enter 0.7071. For the first and second values, and 0 for the third. Now, pressing apply will compute the appropriate coefficients for the global coordinate system, and then enter the appropriate values in the resistance values in the panel above. And we can see what the inertial resistance values are in the panel above, corresponding to the values for the principal axes in the porous media. And now we can press OK. Next, we will see the Stator blade source term panel. We can enable this option and highlight it to see its controls. We'll apply the source term to cell group number 2, so at the top of this panel we can enter a 2. In this case, we want to turn the flow through 135 degrees from its initial direction. So we enter a unit vector corresponding to this new direction that's measured from the horizontal plus x direction. In this case, the unit vector is as follows: negative 0.7071 for the x component. For the y component is 0.7071. And we can leave the z component set to 0. In this case, we'll enter a domain length of 0.1 meters. In this case, we can set the drag coefficient to 0, and we can apply the source term to the local velocity, and press OK. Next, we'll see the initial conditions action tree panel. In this case, we'll choose the option to initialize the entire domain, and we'll choose the temperature-based option. Here, we'll need to press the green plus sign to add an initial condition information set. We'll highlight that, enable it, and enter the following values. For the static pressure, we'll enter 101,325. Temperature, we'll set to 288 Kelvin. For the U component of velocity, we'll enter 25 meters per second. And for V and W, we'll leave those set to 0. We'll also wait to initialize the turbulence values. And at the bottom of this panel, we can press OK. Next, we'll see the boundary conditions action panel. We can focus our attention to the information trees. In this case, we see a groups tree and a boundary families information tree. We can also toggle the 2D grid display in the toolbar. In the groups information tree, we can highlight group number 2 to identify its location within the domain. And cell group number 1 is everything except this small region. The source terms will be active in cell group 2. Also in the information tree is the boundary families tree. Here we can view the individual boundaries that are applied in this case. You'll also notice that we can highlight the individual boundaries to identify their location within the domain. Once we set the boundary conditions for each boundary, we'll see a green check mark replace each of the red X's. Now we'll set up each of the boundary conditions. The BC named wall will be set to type wall, so we can drag that BC over to the wall category. Here we can choose viscous, wall function, adiabatic, and stationary with respect to mesh motion. And we can leave the remaining options unchecked and press OK. Next, we will drag the BC named outer to the open category. We will keep the boundary condition subgroup set to inflow and outflow. The type of information specified will be pressure and temperature. The condition applied will be inside velocity, and there will be no additional information, so we can leave that set to none. Here we'll need to press the green plus sign to create an information set. You can highlight that and enter the following values. For pressure, 101,325 pascals. For temperature, we can set that to 288 Kelvin. And we can keep the other default settings. We'll set the turbulence quantities at a later time. And press OK. Next, we'll drag the BC named inlet to the open category. For the boundary condition subgroup, we will choose inflow only. We'll also choose pressure and temperature for the information type. We'll keep the stagnation pressure and temperature option applied. Next, we'll press the green plus sign to create a new information set for this type of BC. You can highlight that. We'll enter the following values for total pressure and temperature. 130,000 pascals. And temperature will be set to 500 Kelvin. And we can keep the other options in this panel set to their default state and press OK. And once we set all the boundary conditions, we can see that they all show green check marks, and we can press OK at the bottom of the boundary conditions panel. And next we will see the turbulence control action tree panel. We can accept all the default settings here and press OK. Next we will see the turbulence initialization action tree panel. Here we will need to initialize the turbulence quantities for each information set. So we can right click the first information set in the list to open its panel. This information set corresponds to the initial conditions. We'll choose yes at the top of this panel to indicate that we know the turbulence length scale. Here we can set the turbulence level suggestion set to none. And we can set the free stream turbulence level set to 0.16. We can set the turbulent length scale to 0.001, and we can set the free stream velocity to 25 meters per second. And compute will show us the values of k and epsilon that will be applied in the initial conditions. We can press OK and OK to accept these quantities. And we can continue down and press OK to the pop-up box notifying us that we don't have an explicit velocity that's associated with this boundary condition. We can right click on this so that we can specify the turbulence quantities for this boundary. We can choose yes at the top of this panel to indicate that we know the turbulence length scale. We can keep the option below set to none. For the free stream turbulence level, we can set that to 0.01. For the turbulence length scale, we can set that to 0.005. And for the free stream velocity, we can set that to 20 meters per second. Press compute, OK, and OK again to accept those values. Next we can highlight the last information set, press OK in the pop-up box, right click to open up the entry panel. Here we can choose yes at the top of this panel. We can keep the option set to none. We can enter a free stream turbulence level of 0.02, turbulence length scale set to 0.005, and a free stream velocity set to 150 meters per second. Press compute, OK, and OK again. Next we can accept all the values set for the turbulence initialization by pressing OK. Next we see a panel prompting us to choose if we want help setting up the numerical options. We can select yes at the top. In this case we'll select a flow regime that is subsonic. For the numerical setting assistance, we can keep the Riemann solver and time integration options selected. In this case we'll choose internal flow. We'll set an approximate system velocity set to 200 meters per second. And we'll keep all other options in their default state and press OK. Next we will see the Riemann solver panel. We can open the preconditioning controls by pressing the plus sign. In this case we'll enter a approximate system velocity of 200 meters per second, and we'll accept all the other defaults and press OK. Next we'll see the simulation strategy panel. We'll choose no for doing a restart. We can keep the integration type set to implicit. The number of global steps we can leave at 750, and we can keep the convergence criteria set to 5 orders of magnitude. And we can keep the other default settings and press OK. Next we will see the time integration control panel. We will reduce the CFL number from 100 to 50. And under the advanced control options, we can reduce the temporal smoothing factor from 0.75 to 0.5. And at the bottom of this panel, we can press OK. Next, we'll see the spatial discretization panel. In this case, we want to make sure that we're running in second order mode. We also want to choose a 2D polynomial option. In this case, this is not an axisymmetric case. We'll keep it at standard 2D polynomial settings. And we can review the advanced control options and accept all the default settings and press OK. So next we'll see the neutral plot file options panel. In this case, the default variables that we'll be able to display in the visualizer include pressure, velocity, magnitude, static temperature, density, etc. We can accept these and press OK. At the pop-up box, we'll see an option for whether or not we want to copy the neutral plot options file to the plotting options file. We can press OK. Next we'll see the probe and output options file. We can accept the default settings and press OK. So this completes the problem setup, and we are now prompted to save the input file. We can do this now by pressing OK. After running this case, we can complete the remaining parts of this tutorial by enabling the various source terms that were set up previously and running each of those cases individually. So this case is ready to run, and we can run the case from the menu bar by going to the Tools menu. At the bottom we see the Run CFD++ option. In this case we'll run in double precision with a single CPU, and we can start the case by pressing the Run button. And we now see that the case is running and the solution and plotting files are being written to our working directory. For more information about post-processing and visualization, you can refer to the results section of this example. And this completes the thrust reverser tutorial. Thank you.